So I'm Madhu Rangarajan. I'm a principal engineer in the cloud service provider group. Rob Cohn was supposed to join me today, but he's not doing well, so I'm going to give this talk on my own. And I'm going to be going over networking trends in cloud, and I'm going to be using examples from public domain information available from multiple leading cloud service providers as I go through this talk. Yep, next slide, please. Maybe full screen.
This
Yeah, we're trying to fix something. And okay, again. There. Actually, if you could go back to the previous slide. So I'll give an overview of how Intel views the cloud market, and yes. And then I'll talk about some network topologies in the cloud and implications to what that means to different networking functions. And I'm going to deep dive into infrastructure as a service and how software-defined networking is evolving in that space. And then I'm going to talk a little bit about future of NICs and how FPGAs are increasingly being used in the data center for networking. Next slide, please. So just to give you a quick overview of how Intel views cloud. The cloud, of course, is very heterogeneous and it's vast, right? And the way we try to classify cloud service providers is we kind of look at infrastructure as a service. This is the first column, where you have cloud service providers hosting VMs and containers to end customers. We have tiered software as a service, where you have data centers that are optimized to deliver a very specific application. Facebook is a good example of that. And then you have hyper-converged software as a service, which are data centers that offer a whole bunch of different software services kind of running on uniform infrastructure. Now, if you look at software-defined networking in general, infrastructure as a service providers started really deploying software-defined networking at scale and started innovating quite a bit on that. We are also starting to see hyper-converged software as a service providers starting to look at software-defined networking as something very important to deliver differentiated services. And of course, and to those who have been following some of the developments in infrastructure as a service, the biggest players in that space actually started deploying smart NICs, and we'll talk about some examples. Slide, please. So in terms of network topologies, actually the full slide isn't visible. Beautiful. Actually, I can. View. Okay, maybe just zoom out slightly. So, yeah, that's good. All right. So if you look at the predominant topologies for networking we find in large-scale data centers, folded class is probably the most common topology we see in many data centers. So I won't spend too much time describing the topology. I'll make those slides available, and I've also placed a link. This is actually a paper from Facebook, and they describe this in detail. But you have a bunch of racks, and you have some oversubscription at the rack with a bunch of servers. And then from the rack, you go to a leaf switch and a spine switch. And the leaf and spine layers are not fully connected. So what ends up happening is you have a whole bunch of different zones in the data center. And in this tiered kind of structure, you have a lot more zones in your data center, and you tend to try and limit your traffic either within a rack or contain it within a zone. And it costs less, clearly, because you don't need as many switch ports, but it requires a lot more control over the workload distribution. So if you have a very specific workload that you are very familiar with, this topology works pretty well because you can orchestrate your workload exactly the way you need to kind of keep the traffic within the rack or within the zone. On the other hand, there is a fully routed class topology, and again, this picture should be familiar if you've looked at some of the Google papers in the past. In this topology, there tends to be very little oversubscription at the rack. Often it's 1-to-1. And then at the leaf and the spine layers, things are fully connected. So as you can see, this will need a lot of switch ports, but the result is there's extremely high east-west bandwidth and uniform latencies across any given nodes in the data center. And there are very few much larger zones. And what this facilitates is much more distributed networking functions. For example, load balancers, or if you're doing SSL termination, instead of doing it at the edge in an SSL proxy, you could distribute it across your compute nodes. So there are various examples of how in these kinds of topologies, things tend to be distributed across the data center. Google's maglev is actually a very good example of this, and there are many white papers on that subject. Yes. Now I'm going to dig a little deeper into infrastructure as a service, because this is where SDN has been an area of innovation. And if you look at what customers are trying to do with infrastructure as a service, they're really trying to rent out as many VMs as possible to their customers, their end customers. And to do that, they want to maximize their VM density on a rack. And you end up having limited number of racks per data center, limited number of nodes per rack, and a limited number of VMs per node. So to maximize that, you want to kind of pretty much use up as many cores as possible for actually for the virtual machine rather than for infrastructure and for other tasks, so that you can sell them. And again, CSP cannot rent out all of the cores in a server for a VM, because there are infrastructure tasks. There could be a vSwitch, there could be storage services, and there could be other infrastructure tasks. But in general, when we look at our different infrastructure as a service customers, what they're trying to optimize is the number of VMs per rack as a first-order proxy. And that kind of takes us to the whole SDN offload concept. Now, the picture on the left here shows what's been most commonly done, which is you have a 2-socket Xeon server. You have a whole bunch of cores in that server. And then you have your software-defined networking / vSwitch running on some of those cores. And you often also have a control plane sitting there, which an orchestration layer can talk to program flow rules and so on. Now, there have been lots of innovations happening in that space. There's DPDK, which significantly reduces the overhead of the vSwitch. We have various companies innovating there to reduce the overhead of that. And because of that, what we've seen is basic functions for the vSwitch can scale anywhere from 1 to 4 cores at 10 gigabits per second, depending on the optimizations, depending on how large your flow tables are. So that number is quite variable, but it really depends on what you're doing. But as your throughput keeps scaling from 10 to 25 to 50 to 100, we are starting to see a trend of customers doing things that look more like the picture in the middle and the right, where they want to offload as much of the SDN and vSwitch as possible to a NIC. And this is kind of what we're calling an iNIC or a PNIC, an intelligent or programmable NIC, or I think some people like to call it a smart NIC. And again, there are two models. One is where you have a trusted host and the control plane is still staying in the hypervisor. The other is where you have an untrusted host and everything is controlled from the network side. So really, these are three different models for deploying a vSwitch on a node for software-defined networking. And different cloud service providers have different thresholds, different TCO models. So when they would flip from the middle, from the left model to something in the middle or to the right, is really completely dependent on their TCO model. And some of them may not flip because there are clearly trade-offs. And we'll talk about some of those trade-offs in the upcoming. And the other offload that's becoming really useful in scale-out infrastructure as a service deployment is RDMA. Now, traditionally, we're used to thinking of RDMA as something for high-performance computing clusters, for low-latency networking for HPC applications. But for infrastructure as a service, the main use case is for storage, especially with the storage media speed going up significantly and storage forming a significant part of your data center traffic. Pushing storage traffic over the network requires a lot of CPU utilization. And especially as you start getting congested on the network, if you use TCP for storage, as congestion increases and as retries increase and so on, your CPU utilization starts going up significantly, and you have a long latency tail. And that's what RDMA helps with significantly, because with RDMA, you can essentially do storage over your network with zero CPU utilization. And as I was talking about earlier, zero CPU utilization means you now have more cores available to rent out to an end customer and generate revenue. And also the higher speed media is also driving larger network throughputs, and that makes RDMA even more useful. And the other use case for RDMA beyond storage is also as a transport for things like RPC calls. So again, minimize the overhead of all of that. And again, there are multiple flavors and implementations of RDMA. There's Rocky V2, there's IWARP. But beyond the RDMA protocol itself, there are also multiple congestion management schemes. And some of these have white papers published on the internet, like Microsoft Azure has DCQCN, which is their congestion management scheme to deploy RDMA at scale. Google has Timely for, again, deploying for congestion management at scale. And then there's, of course, DCTCP. Now, as I was talking about the vSwitch, and as I was talking about the RDMA and the different flavors of RDMA and the different methods of doing the control plane, this is not an all-inclusive foil, but this is just to give an idea of how cloud networking has been changing over time. And there's a lot of innovation happening in security, different protocols for inline, different ciphers, different ways of doing storage, compression, deduplication, custom algorithms. RDMA protocols have been changing. RDMA has multiple custom congestion management schemes and so on. Flow tables and tunneling formats have been evolving. There are multiple somewhat standard tunneling formats, but cloud service providers are also doing their own customizations. So there's a whole lot of change happening in this field, and that's why having the flexibility and programmability to be able to change all of this is very important as we go forward. And we'll talk about how you do that, especially if you start looking at offloading things to a NIC. So now you want to have a NIC. You want to offload these SDN and RDMA and congestion management and anything that is infrastructure so that you can maximize revenue to that NIC. But how do you do that and still maintain flexibility? Because as I showed you, the flow table formats are changing, RDMA congestion management schemes, many custom implementations and so on. So really we have kind of three different ways of having flexibility, right? Going from left to right, you could use an FPGA, and we kind of call that a PNIC, a programmable NIC. Now, an FPGA has millions of logic elements, and I'll kind of deep dive into it a little bit in the next while, because it's got extremely high memory and network bandwidth, and you can create a fully custom pipeline there. And it's capable of compute and network acceleration, but we'll really focus on the network acceleration piece here. So that's one way to do custom vSwitches and custom congestion management and so on. Of course, FPGAs are a little bit harder to program than software. That kind of takes us to, but it's much more efficient and tends to be at the speed of hardware. You don't have to deal with interrupts and software level latencies and so on. Then you have NPUs, which have typically a sea of cores where you do the packet processing. This is another approach. You can use things like DPDK and do your packet processing there. But they often use specialized environments like micro engines and so on. So they are a little easier to program, but not quite as easy as programming an IA core. And then, of course, you have the CPU itself. You can, and we heard from Google the innovations they have made moving to user mode vSwitches, reducing the overhead of the vSwitch and so on. So that's another way to do it. But really, there are trade-offs, right? The trade-offs are what's the infrastructure tax, as in how many cores are used up by the infrastructure function and not available for VMs anymore. So depending on the option, that number could vary. The ease of programmability is clearly different. FPGA, if you want efficient code, you probably need to write RTL. Whereas if with the CPU, you can just write C code with some optimizations. Then there's, of course, jitter and predictable behavior. When you do things in hardware, the jitter tends to be less. In software, unless you're extremely finely tuned, there can be a little more jitter. And then the power/performance trade-offs. So FPGAs are pretty power efficient. So if you go from ASIC to CPU, ASICs are generally the lowest power. FPGAs are somewhere in between, and CPUs are a little bit higher. So you're really trading off flexibility and power performance and ease of programmability to decide what option you want to go with. Now, this is just a quick overview of what an FPGA has in it. I won't spend too much time on it. I'll make these available. And if you go to Intel's website and click through to PSG, you can find a whole lot of details on FPGAs. But really, what an FPGA has is a whole bunch of partially reconfigurable regions where you can place different IPs that can be updated. You have a PCIe host interface, which has both hardened and some soft elements. You got these millions of logic elements that can be reprogrammed, and there are high-level ways of programming it like OpenCL, which works well for some applications, and there are low-level ways of programming it using RTL. Then you have memory interfaces, so you can have a few channels of DDR depending on your application. You have a network interface, so it has a MAC-PHY, so the FPGAs we have can do 100 gig or more greater networking. You got lots of memory blocks, lots of SRAMs spread throughout the FPGA that you can use to buffer things and create your logic blocks. And you also have DSP blocks to do any compute-intensive functions. So for example, if you had any floating point you wanted to do for any of the use cases, you can use the DSP blocks for that. Now, in terms of the data center accelerator use cases for FPGA, what we are primarily focusing on is the picture on the left, where if you want to offload the vSwitch to the FPGA, you can actually implement that as a programmable pipeline on the FPGA itself and do all of your inline processing there. So now, essentially, you have a programmable entity that has the performance of hardware with some level of programmability. It's not as easy as programming software, but it is quite flexible. But of course, the FPGA can also, it's a flexible piece of hardware, so it can also be used for look-aside acceleration. For example, you wanted to implement your own custom compression algorithm. You could do that on the FPGA to get better performance. That's Lucaside accelerator. And if your FPGA was large enough, you could also combine them and support both. For example, if you wanted to do storage compression, you could have both of them in the same accelerator, do one of them as a Lucaside, and send them over the network inline. So this is probably the most famous example of how an FPGA has been used in the data center for software-defined networking. So what this is Microsoft's Catapult FPGA, where they had a NIC with a Stratix connected to a Stratix 5 FPGA as a bump in the wire. And so the data flow is packets go from the CPU to the NIC, from the NIC to the FPGA. The CPU programs whatever rules need to be programmed on the FPGA directly through the other PCIe interface. And then the FPGA applies the policies on the packet, any NCAP, DCAP, ACLs, and so on, and then sends it out over the network. And of course, if you read the white paper that I linked to in this slide set, they also talk about using the FPGA for other accelerators. And I think the most useful feature of the FPGA from Microsoft's perspective was the fact that in their infrastructure as a service kind of use case, they could load up a bit stream in the FPGA that does the vSwitch and SDN offload. And when they're using it for search, they can reprogram this FPGA and do search indexing and other search-related offload. So they can use the same hardware for multiple purposes. So if you think of the Xeon CPU as the best general-purpose software engine, you have an FPGA as kind of a general-purpose hardware engine for deploying multiple accelerators that need the performance of hardware. And just to take away and just summarize, I think I kind of spoke broadly about many things, but just to summarize, networking has really become an innovation vector for CSPs, especially as they scale out, as they're deploying and trying to maximize their VM density, offer quality of service, offer the right level of networking services. They're innovating in many different ways. They're creating their own flow table formats. They're creating their own vSwitches, and so on. We expect inline infrastructure and application acceleration to grow into the future, mainly because, well, there's more happening in the vSwitch, especially as we start talking about containers and different ways of deploying containers. There's a lot of innovation happening in security and isolation and so on. So we expect innovation to continue in the space. So it's going to be very hard to fit that into fixed function ASICs. And of course, as Intel is going to have multiple options to continue to facilitate this innovation. So we are going to continue to have our ASIC NIC roadmap, which will be the optimal power and performance solution for known IP. So if you want standard NIC functions, that will be your lowest power performance and highest performance solution. You want maximum flexibility and be able to modify your vSwitch, then we still have our general purpose CPU and Xeon, and we have user mode DPDK vSwitches. So we're going to continue to improve on that, add features to our CPU to facilitate that. And now we also have an FPGA in our portfolio with the acquisition of Altera last year, where we can now enable innovation with even better power, performance and power characteristics than a CPU for some of these applications. The questions? Yeah.
The FPGA use cases that you mentioned about 3 slides ago, do you need to reconfigure the FPGAs, or can you do partial reconfiguration?
So partial reconfiguration is something that we have not enabled yet. It is in the process of being enabled. So for now, you can reconfigure it, but it kind of requires a reboot. It's not reprogrammed while the system's powered on.
Okay, it's sort of like a start time reconfig. Okay, got it.
Yeah.
Second, are these all PCIe interfaced FPGAs, or are some of them coherent memory or coherent bus FPGAs, i.e. QPI?
So we have both options. So we have FPGAs that can plug into standard PCIe card form factors. And we also have the Xeon plus FPGA MCP product that you might have heard of in announcements. And that's going to be a Xeon co-packaged with an FPGA, and that's going to be connected using a coherent interface.
Okay, and last question. Some of these are Intel innovations. Is Intel enabling third parties to put IP onto the FPGAs?
Well, stay tuned.
The PCIe, is there any evolution coming on that?
Well, there is a standard Gen 3, Gen 4 PCIe evolution that's going to happen gen over gen. You must have heard of all of the other coherent interconnects that our competitors are talking about. Mm-hmm. And we are talking about what options we will enable, but yeah, nothing that we can talk about yet.
Okay. The second question, last one, is you mentioned about the RDMA. So if we have to use a zero copy memory between the CPU, are there any additional facilities available today?
You mean you want to do a peer-to-peer
DMA?
Peer-to-peer
common memory.
So not on an Intel NIC today, but that's something we are looking into, because peer-to-peer DMA is really something that is supported by the CPU and the PCIe ports. You have to do it, you have to orchestrate it through the driver, and that requires two different drivers to work with each other and so on. And yeah. So nothing technically prevents it on the platform, but I don't think an Intel NIC will work with a GPU in that manner. Any other questions? Any questions on the bridge? All right, thanks.
Okay, so, nope, not another talk, but we have idea roulette still. So who wants to play? Come on. Everybody took cards. Donna, you need their arms.
Hey, we also have raffle prizes, and you need to be present here to get those.